think we want to look at the laboratory that's in your book labeled as 1-1B, determine the wavelength of red light. Let's talk about what we have here on the board. I think it's important that we look at some of the parameters. When we refer to lambda, lambda stands for wavelength. D in this equation that we have stated for calculating wavelength is going to be the spacing in the gradient. M is an integer number of spots used in the equation. We're going to use one spot, but depending on the number of spots will depend on the diffraction angle. If we just take a look a bit of what we have on the board, and then I'm going to actually take the measurements on the equipment. We have a drawing of a diode laser, the beam passing through a diffraction or interference grating, depending on how you want to view that. This is going to produce diffraction spots, and there's going to be a series of these diffraction spots. We're going to look at the diffraction angle, and we're going to look at the separation between the central spot and the first spot, and that would be the same on either side of that central spot. Another important number that we need to look at is what is the spacing in the gradient itself between the lines, and we selected a gradient that is 0.0033 centimeters. We're going to do things in centimeters. They're going to be easier to look at in regards to the rulers and the meter sticks we're going to use, but later on we'll just convert back into meters if we need to. Another important measurement is the distance from the gradient itself, diffraction gradient itself, down to the pattern which we have labeled as L. Okay, I think what we're going to do now, we're going to come around and look at some of the equipment. First, let me, before we actually take a measurement, again, what we have on the board now, you're seeing actually set up as an experiment. Here we have our laser, our diode laser. Down from the diode laser, we have the diffraction gradient. Down from the diffraction grating, you're going to see a distance to the table, and when I put the lights out, there's going to be a meter stick that we can take a measurement of what we call delta X, the distance between the central spot and the next spot on either side. But before we do that, I think I'm going to take one measurement first, and we're going to look at that measurement, and that's what we call L. And that's the distance from the gradient to the table, and that just about is 82.5 centimeters, okay? So we need to know that number, 82.5 centimeters, and let's put that on the board, because we do know that number now. That number is 82.5 centimeters for L. We'll have to put the lights out and look at the pattern that's now produced by the diffraction gradient. And you'll see the central spot. You'll see a number of spots, order of spots. But what we call delta X is the distance between the central spot and the next spot over. Looking at that meter stick, we're looking at that to be about 1.7 centimeters. Again, from this point to this point is 1.7 centimeters. Now, depending on the order of spots that you would like to use, that will be determined the diffraction angle. We're only going to use the first spot, but you could go from the central spot to the third spot or to the fourth spot, and obviously that angle is going to increase depending on the number of diffraction spots you're using. But again, we're going from the central spot to the first spot. Let me put that number on the board. We said we have 1.7 centimeters for the distance between the central spot and the next spot, 85.25 centimeters. Now what we want to do, we want to figure out what this angle is. Theta will be 1.7 centimeters, right, divided by 82.5 centimeters. And when we plug that into our calculator, what we're going to find out is that we do have an angle of 1.18 degrees, 1.18 degrees, okay? And actually what you're doing here is you're really calculating for this angle. Again, this is L right here, this is delta X right here, and you're looking at that angle. And you're going to use tangent function. I think you people realize that. Okay, now what we need to do is take all this data and plug it into our expression here for calculating lambda. And the expression is, as we talked about previously, d times the sine of theta, which we now know is 1.18 degrees, times the order, the number of bright spots that we're using. We said diffraction order is going to be 1. So let's put these numbers in. We know this to be 0.0033 centimeters. We know the angle is 1.18 degrees. Okay. And we know that the order is 1. All right, if we put this into our calculator, and let's do that. Okay, we come out with a wavelength as being 6.79 times 10 to the negative 5th centimeters, which is 6.79 times 10 to the negative 7th meters, which is 679 nanometers. And yeah, this is very close to a diode laser's wavelength, and the number seems to be right on target. So here we're using macroscopic type of measurements to come out with a very small value for wavelength. And again, we can do this experiment a number of times. What would we change? We would change the number of diffraction spots we're working with. This number would change 1.7. 1.7 is going to change this angle in here. The length of the distance between the gradient and the pattern stays the same. But however, we can do this a number of times, get a number of values, and then add them all together and get an average. Okay, I think what we need now to do is to just look at this once or twice, and once you do, and when you come to the college, you'll be able to actually perform this experiment. Thank you.